Today, we're going to uncover how a simple ranking system, you could call it a chemical league table, is secretly the key behind one of the biggest industrial processes on the entire planet, getting pure metal from a chunk of rock.
I mean, it's a really good question when you stop and think about it, right? Why is aluminum, which is everywhere in the Earth's crust, so ridiculously hard to produce, and yet gold, which is incredibly rare, can literally just be found lying around? Well, the answer is surprisingly simple.
And here it is. This is the key to the whole puzzle, the reactivity series. You should think of this as the official rulebook. It tells us which metals are, aggressive and love to combine with other elements, and which ones are more laid back and prefer to be alone. Seriously, this one list dictates everything.
Okay, so let's start at the very top of that list. We're talking about the really high-energy metals, the ones that just have to be in a relationship with another element. Think potassium, calcium, and yeah, the aluminum that's in your soda can.
The more reactive a metal is, the more desperately it clings to other elements, especially oxygen, and that bond is incredibly powerful. It really is like a super strong magnet that you just can't pull apart with your bare hands.
Right, because that bond is so strong, a simple little tap isn't going to do anything. You can't just gently coax them apart. You need to bring in the big guns, a method with enough brute force to just shatter that magnetic attraction.
And honestly, this is the perfect way to describe it. Forcing two things apart that desperately want to be together, well, that takes a huge amount of energy, which makes it a very expensive process. And that process is called electrolysis.
So how does this divorce actually work? Well, first, you have to melt the rock, the ore, into a liquid. Then you zap it with a colossal amount of electricity. This powerful current is what finally provides enough energy to force the metal and the oxygen atoms to break up, leaving you with the pure metal you were after all along.
All right, so let's move down the list to the middle of the pack. Now we're in the territory of common metals, like iron, zinc, and copper. Now, they're reactive for sure, but they're not quite as clingy as those drama queens at the top.
And because their bond with oxygen is just a bit weaker, we don't have to pull out that super high-energy, super expensive tool of electrolysis. We can be smarter about it. We can use a little bit of chemical cunning instead of just brute force.
So here's the clever trick. We find an element that's even more reactive than the metal we want. And for this job, our hero is carbon. It turns out that carbon is higher up the reactivity series than iron. It has a stronger magnetic pull for oxygen.
And this is the crucial point. When you heat up the iron ore with carbon, the carbon looks at the oxygen that's bonded to the iron and basically says, hey, I want that more than you do. It just waltzes right in and steals the oxygen atom away from the iron. It's a total chemical heist.
This whole process is called reduction, and it's basically what's happening inside a giant blast furnace. You cook the iron ore with carbon, the carbon swoops in and snags the oxygen to make carbon dioxide, and what's left behind? Beautiful, pure, molten iron. Way more efficient.
Okay, now let's journey all the way to the other end of the list. We're talking about the really chill, unbothered metal world. The ones that, frankly, don't really care about bonding with anyone.
Yep, we're talking about the precious metals, gold, silver, and platinum. They are the complete opposite of those clingy metals at the top. They're so unreactive, so stable, that they just prefer to be on their own. Hey, remember our divorce analogy? Well, these metals, they never even got married in the first place. They are so unreactive that they don't form strong bonds with oxygen at all. They're just found hanging out by themselves in nature.
And because of that, you don't need some complex chemical factory to get them. This is exactly why you can literally find little nuggets of pure gold in a riverbed. They already exist in their pure elemental form. No chemical separation needed.
So, let's bring all this together now. We've seen the high-energy divorces, the clever chemical heists, and the metals that were happy being single all along. What's the one big idea that ties it all together?
This chart just sums it up perfectly. You've got high reactivity, like potassium, you need high-energy electrolysis. You've got medium reactivity, like iron, you can get away with medium energy reduction using carbon. And then you've got low reactivity, like gold, well, it's often found pure, which means it takes very little energy to obtain.
And that's really the bottom line. A metal's position on this one list, the reactivity series, directly tells you how much energy, how much effort, and how much money it's going to take to extract it from its ore. It's really that simple. It's this beautiful, direct link between a basic chemical property and a massive global industry. So it really makes you wonder, doesn't it?
This simple ranking system dictates so much about the world we've built. What other invisible rulebooks or hidden hierarchies are out there, quietly shaping everything around us? Definitely something to think about.